Hello students, in this video we'll discuss wave propagation in an elastic medium. So let's be given an elastic medium. In this case, I'm just going to assume it's going to be a one-dimensional sort of thing. So there's going to be a medium that's elastic. Okay, and I can do this in higher dimensions as well. It's just the PDE works out a little bit nicer in one dimensions, which is one-dimensional, and we wish to understand the existence of wave-like motion in this medium. Okay, and so what's the idea behind this? So let q of x be a non-negative function which is the coefficient of elasticity at the point x. Okay, now we're going to consider the following partial differential equation. Consider the wave equation, consider the modified wave equation. So what's our wave equation going to look like? Well, we're going to write down our typical wave equation, which is this: utt is equal to c squared uxx, with initial data u of x0 is given by something g of x, and x0 is given by some function h of x, right? And now we're going to modify this in the following way. I'm going to say this is going to be negative qxu, okay? And so just a remark over here that this sort of looks very, very similar to me to the Schrodinger equation, right? The Schrodinger equation, of course, in quantum mechanics, you'd have something like this. Just draw the connection, right? It'd be I ut, so it's not two time derivatives, it's not hyperbolic anymore, it's parabolic. Utt is uxx, good enough, and then minus v of x times u, where v is a potential over here, right? So that Schrodinger equation, and it's sort of the same sort of underlying structure, I'm sure what I'm trying to say, except for this is a wave-like pattern, whereas that's like for a flow or a probability distribution, okay? Excellent. We'll talk about Schrodinger a lot in further videos. All right. So that's the point. And so what I want to do now is the following. So of course, it's easier to start with hyperbolic problems in one dimension, because hyperbolic problems in one dimension, there's a finite speed of propagation. So I know the characteristic lines, I know the domain of influence, the range of influence, I know where the PDE is emanating from, I know exactly how to track it. With something like this, with a parabolic problem, there's infinite speed of propagation. So I have to be very, very cautious with how I track things. Okay, excellent. So now what we want to do is we want to analyze this thing, and I want to ask questions, but what we can easily say is we're going to consider an energy for this. So let's define the energy ET, which is 1/2 the integral over r of ut squared plus ux squared, with a c, of course. I need a c squared there. And then I need a what? I need a q plus q of x u squared dx, okay? Now what's the key feature of this energy? Since q of x is greater than or equal to 0, that's going to imply that the energy E of t is always greater than or equal to 0, which is what we need. We need energy to be greater than or equal to 0, right? I don't want negative energy, okay? And so now to prove there's a conservation of energy, let's formally differentiate E, right? So as E prime of t, E prime of t over here, the halves are going to come down and kill that 1/2, and the integral over r, a ut, then a utt, then a c squared, and then a what? A c squared, and then a uxt, and then I'm going to have a plus q of x u of t times u dx. Okay? I'm going to integrate by parts on this term over here, right? And then what? And then, let's see. I might have to change my sign in a second. We'll figure this out, because there's always an issue with this sign. That's going to be the only the only bad thing over here, right? And so what are we going to have? If I integrate by parts on this thing, this is equal to the integral over r ut. It has a ut in it. Then I'm going to have a utt. And then I'm going to have a what? Oh, that's fine, I guess, good. Then I'm going to have a, that's going to be a minus. So I'm going to throw on the other side of the equation, right? So this is going to be a minus over here. So then I'm going to have a plus, minus rather, minus c squared u xx, okay? And that's going to be a plus q of x times u, right? And I probably have to change my sign here. That's a good illustration of this method, how this method works. And so, of course, I want to show that this is equal to 0. If I throw the c over there and the q over there, what do we get? Yeah, so this works. So I throw the c over here, right? And that gives me a negative sign. I throw the q over there, it gives me a positive sign. And that's just the PDE, right? So this over here is just our PDE. And so that is equal to 0. And so we have a conservation of energy in the system, right? So there's a conservation of energy. So that says that E of t is equal to E of 0, okay? Okay. Now let me suppose, and so here's a proposition. Solutions to this PDE are unique, okay, if they exist. And what's the standard method to do this? If U1 and U2 solve, let's call it star, solve star, then so does, it's linear, then that implies that W equals U1 minus U2 solve star with 0 initial conditions. Okay. Well, of course, that says the energy of W at 0 is nothing. And that says by conservation of energy, the energy of W at time t is still nothing. So that says that W has no energy. So W is identically what? W has to be identically equal to 0 because it's a non-negative thing. So W is identically equal to 0. And that implies that U1 is identically equal to U2. And so from this conservation of energy, we're able to derive that there's going to be at least, if there is a solution to this problem over here, then there has to be exactly one solution, right? So you can't have multiple solutions to this thing, and that's important from a physical perspective. You always want to construct a problem. You may not know the solution exists, but you like to show that if the solution exists, there can only be one. For a physical system that is a model, you should not have two potential outputs, right? You should have two potential outputs of what the coefficient, what the wave structure is going to look like. You get two different frames. You don't want that. You just want one exact solution, which is the only model that you're going to get. So uniqueness is a very important proposition, and uniqueness comes from these energy methods, which we've seen in previous videos, but now we can extend it to these more general cases where there's not constant coefficients any longer. It's still a very powerful method. Thank you very much.